Far out in Alaska's Aleutian chain lies a cluster of volcanic islands so small and remote that few people could pinpoint them on a map. Yet beneath these lonely peaks, scientists have uncovered one of the most astonishing geological secrets of the decade. The islands of the Four Mountains, 6 rugged volcanoes rising from the North Pacific, may actually be fragments of something far larger, older, and vastly more powerful than anyone imagined. Recent research suggests that they could be the broken rim of a hidden supervolcano, an immense blast zone buried under the sea and masked by younger eruptions. If true, it would mean a past eruption here rivaled the greatest volcanic blast in human history, scattering ash across continents and reshaping the very landscape of the Aleutians. But how does a supervolcano remain invisible for thousands of years? What clues were buried in the ocean floor, the ash layers of Greenland, and the restless activity of Mount Cleveland that finally exposed its existence? And what does this discovery mean for the future of the North Pacific? Today, let's delve into the hidden supervolcano beneath Alaska. Don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. The Aleutian Arc is one of the most dynamic volcanic systems on the planet. Stretching more than 1,900 kilometers across the North Pacific, it forms where the Pacific Plate plunges beneath the North American Plate. This subduction process melts rock deep within the mantle, generating magma that rises to feed a chain of more than 80 volcanoes. Many of these are active, from the frequently restless Shishaldin and Pavlov in the east to the towering stratovolcanoes of Tanaga and Okmok farther west. A few erupt frequently. Only a handful, however, show the kind of explosive energy capable of altering global climate. The central Aleutians are particularly volatile because of rapid subduction, steep slab angles, and the availability of both oceanic crust and volatile rich sediments to fuel magma formation. Within this fiery arc, the islands of the Four Mountains, home to 6 volcanoes, Cleveland, Carlisle, Herbert, Tana, Chuginadoc, and Uliaga, occupy an unusually compact arrangement. Spread across less than 50 kilometers, they form a tight circular cluster rather than a linear chain. Their steep volcanic cones rise from deep ocean basins, built atop older submarine lava flows and pyroclastic layers. Beneath these relatively young volcanic cones, however, lies a far older and more complex structure marked by collapse scars, ring faults, and a broad buried depression. Magma intrusions have repeatedly reshaped the crust, obscuring the deeper system, but new imaging now reveals a landscape molded by one dominant event: the formation of a massive caldera that indicates the presence of a long-hidden supervolcano. The idea that the central Aleutians hide a supervolcano began with a simple observation. The islands form a near-perfect arc, curving around an invisible center rather than aligning in a straight volcanic chain. This unusual geometry suggested the outline of a vast crater. Early bathymetric maps strengthened the suspicion, revealing a broad depression between the islands that lacked the typical symmetry of normal ocean basins. As high-resolution sonar improved, scientists identified terraces and structural boundaries resembling the submerged walls of a caldera more than 18 kilometers across. Gravity surveys offered even stronger evidence. Beneath the islands of the Four Mountains lies a pronounced low-density zone, consistent with crust that collapsed during a massive eruptive event. The anomaly is far too large to be produced by any single volcano. Magnetic data helps define the caldera's approximate width, up to 23 kilometers, placing it among the major caldera systems of the world. TAFRA studies then added the most startling clue: ash layers found across Alaska, Canada, and even Greenland match the chemical fingerprints of Aleutian magma. The sheer volume of this ash exceeds the output of all known eruptions in the region, pointing to a prehistoric blast of monumental scale. Meanwhile, satellite deformation data shows portions of the islands rising and falling together, responding to pressure changes within a shared magma reservoir. Together, these findings reveal that thousands of years ago, a VEI-6 or VEI-7 eruption emptied a massive magma chamber, collapsing the crust and forming a caldera now hidden beneath younger cones. Its size and inferred magma volume suggest a system capable of eruptions rivaling Mount Mazama or Novarupta, making this newly found caldera one of the most powerful volcanic structures in the Aleutian Arc. Following the ancient caldera-forming eruption, the islands of the Four Mountains did not settle into long-term dormancy. Magma continued to push upward along ring faults, building the younger volcanic cones that now define the landscape. Geological layers of ash preserved in surrounding marine sediments reveal a long pattern of quiet intervals, punctuated by renewed episodes of volcanic activity, a cycle that has persisted for thousands of years. Among these younger cones, Mount Cleveland quickly emerged as the most energetic. Its structure rests on older volcanic deposits tied to the caldera, marking it as a rejuvenated vent positioned directly on the supervolcano's rim and ideally placed to respond to deeper shifts within the shared magma reservoir. Its long-term behavior underscores this role. Since 2000 alone, Mount Cleveland has erupted more than 60 times, producing sudden, short-lived explosive events marked by ash plumes and volatile-rich magma surges. This eruptive tempo continued into 2024 and 2025, when satellites recorded intermittent ash bursts, steam emissions, and elevated sulfur dioxide. Several aviation advisories were issued across the North Pacific Flight Corridor, illustrating how even modest unrest at Cleveland can ripple across global routes. Seismic swarms beneath the island group further suggested magma transport at depth, with tremors occasionally migrating between islands in a manner consistent with a connected magmatic system. Because of its position, frequency of activity, and sensitivity to deep pressure shifts, Mount Cleveland functions as the system's primary surface warning beacon. It is the volcano most likely to signal early changes within the underlying supervolcano. While recent activity does not indicate an imminent major eruption, Cleveland's behavior offers an indispensable window into the evolving dynamics of one of the most powerful volcanic systems in the Aleutian Arc. Although no scientist suggests that a super eruption is imminent, the potential consequences of such an event demand attention. Evidence of a past VEI-6 or VEI-7 eruption shows what this system is capable of. A new caldera-scale eruption would be catastrophic, ejecting vast quantities of ash across Alaska, Western Canada, and possibly the continental United States. Ash clouds could shut down aviation throughout the Pacific Basin, severing routes between Asia and North America. Pyroclastic flows entering the ocean could generate tsunamis affecting coastlines from Alaska to Hawaii and even Japan. Globally, sulfur aerosols lofted into the stratosphere could cool the climate for months or years, disrupting weather patterns and agriculture. North Pacific fisheries, critical to regional economies and global food supplies, could be devastated as ash covers marine ecosystems. Despite the Aleutians' remoteness, the effects of a major eruption would radiate worldwide. Even smaller events, as shown by the 1912 Novarupta eruption, can produce far-reaching hazards. The hidden supervolcano beneath the islands of the Four Mountains is therefore not just a local geological curiosity, but a potent reminder that some of Earth's most powerful forces lie in places least accessible for study. Monitoring a submerged and remote volcanic system is one of the greatest challenges in modern volcanology. The nearest permanent instruments are mounted on distant islands, leaving the deep caldera and its magma plumbing largely unobserved. Satellites offer valuable information on heat, ash, and gas, but they cannot detect the subtle seismic signatures that reveal magma movement. Marine expeditions provide excellent data, but they are infrequent and expensive. Scientists are now advocating for expanded seafloor sensor networks to better track seismic activity, deformation, and hydrothermal changes beneath the islands. In recent years, the Alaska Volcano Observatory has increased satellite-based monitoring and collaborated with oceanographic institutions to conduct targeted surveys. Each dataset brings the scientific community closer to confirming the caldera's existence and understanding its behavior. Preparedness plans include aviation alerts, hazard modeling, and eruption forecasting. But the current limitations mean that large-scale unrest could still go undetected until it nears the surface. Improving monitoring in the central Aleutians is therefore essential, not only for scientific advancement, but for global risk management. The discovery of a hidden supervolcano beneath the Aleutian Islands ranks among the most compelling geological findings of the decade. It transforms a small cluster of remote volcanoes into the rim of a colossal, long-buried structure capable of influencing climate and disrupting global systems. Yet much about this system remains uncertain. The caldera is difficult to image, its age debated, and its modern behavior only partly understood. What is certain is that it remains active. Mount Cleveland continues to erupt, seismic tremors pulse through the region, and magma still moves beneath the islands. As technology advances, scientists hope to unravel more of this concealed giant's mysteries. The Aleutians, long a frontier where ocean and fire collide, may hold one of the largest volcanic systems in the North Pacific. Understanding it is vital, for this hidden supervolcano is a sleeping giant whose awakening would command global attention.